Hello, it's Keith here and this is lesson 6 of my x86 assembly programming tutorials. Today we're going to be looking at some more mathematics commands and a few other things we've left out. We've covered the vast majority of commands now on the x86, but of course there's a few more that really are super important. We're going to need to cover them today. So let's go over to the code and have a look at what we'll be doing. Okay, so the first thing we're going to be discussing is using the carry flag and using it to extend a register. Our registers are 16 bits, but there'll be times we want to work in 32 bits, 64 bits, whatever. Now, of course, if you're on the 386, the x64 and things, you've got proper commands to do this, but these are x86 tutorials and we're discussing how the x86 worked around these, so bear with me on that. Okay, now if you're familiar with another system like 650 to Z80, you can probably guess the answer is the carry flag. When you do a mathematical operation, if the calculation exceeds the limit of the registers that it was performed on, the carry flag will be set if an addition went over the limit, and the carry flag will act as a borrow if it went under the limit, if a register went below 0 in a subtraction operation. And that's exactly what we will do here on the x86. So let's fire up this example and let's just see it in action. Okay. So what have we got here? Well, we've got a series of mathematical commands here. First, we've got an add, and then we've got a subtract. And we're using bx and ax here as a pair to perform this operation. So we're effectively simulating a 32-bit pair here. Now, ax is the high part, and bx is the low part. And you can see that the high part's on the left and the low part's on the right. So you can see here, we're repeatedly adding 1 to bx, and also we're adding 1 to ax here because we've got cx and dx as our addition components here. Now you can see here that each time we're adding 1 to ax here, but when bx overflows here, we're actually adding 2 this time, and that's because the carry flag was set just here. So the carry flag is an additional value that is being added as a sort of extra bit here to ax in this part here. And you can see that the exact opposite happens here when it is being treated as a borrow here. Now it might be clear actually if we just change this, and we'll just change the cx part to 0 here, and we'll just run it again. Okay, so this time we're just effectively adding 1 to our pair here. So if I just put this on top here, so you can see ax is unchanged here, and this value here is going up, and when it overflows over 0, the carry flag is set, and then this is being added to ax. And the command that's doing that is this ADC, add with carry command. So add here is affecting the carry, but it's not adding the carry. ADC is adding the value cx to ax and also the carry bit, which is why when this carry bit was set here, a value of 1 was added here, even though the cx component was actually 0. Now in the subtraction, we've got the borrow here, which is what the carry is being treated as. So again, we're subtracting 1 repeatedly from bx here, and ax did contain 1, but as soon as that now borrow flag, which of course is the same thing as carry, is being subtracted with borrow by this command here, then ax becomes 0 and things carry on as normal. So as I say, these two pairs are effectively being treated as 32 bits, and because the carry flag is bridging the gap between those two registers, provided we chain these kind of registers together, we can do an add with carry or a subtract with borrow, and we can extend up to 16, 32, 64, whatever we want. So this is how we can use registers and the carry flag to extend it to much larger values. So there we go. So that's the use of the carry flag. The other thing that's very impressive about the x86 is its multiplication and division commands. Unfortunately, though, they are a little bit complicated. We've got an imul and we've got a mul command. Now imul is a signed multiply, and mul is an unsigned multiply, because remember, depending on whether your registers are being treated as positive and negative or always positive, the commands and the values of a register will vary. In this example, ATH could be 128 positive or 128 negative, depending on whether you treat it as a signed or unsigned number. So we have different commands here. Now, the other slightly tricky thing is that the commands aren't exactly transparent from the opcodes what they're going to do. So we've got imul BL here, but the command implies AX equals AH times BL. This is all implied here, even though it's not specified as part of this command. So you really need to get the cheat sheet here and just check out what these commands are really doing so that you make sure you understand what's going to happen as a result of them, because otherwise they're going to be quite confusing. So say we can specify any register component here, but it's going to be applied to AH. AH is going to be multiplied by the register here, and the value is going to be stored in the 16-bit pair AX, whether we want it to or not, so to speak. So as I say, it's just something you've got to be aware of, and of course you've got to be making sure that you're using the correct signed imul or unsigned mul command, just depending on what you want to do. Now, in this first example, we're going to be using 8-bit values, and in this second example, we're going to be using 16-bit ones. And again, you can see that the operation in this case was using AH because we were specifying an 8-bit part, and in this case it's using AX as the source, but then the destination, the result, is actually being stored in a pair of registers as a 32-bit pair, and so it's being stored in DX as the high part and AX as the low part. Okay, well, let's fire this up and let's see what happens. Okay, so here's our first example here. So we were multiplying hexadecimal 80 as a signed number by 10. Now we've done that, and because of course this is a signed number, it's a negative, all the other bits have had to be set as well, so that has become F800 here. You can see that's worked okay. But of course, if we treat it as an unsigned number, hexadecimal 80 here has become 800 here when we've multiplied it by 10 here. Okay, so that's these examples here. This is the first one just here. This is the second one just here. And then onto the 16-bit ones. Now, as I say, the results are going to be stored in DX as the high part and AX as the low part. So this part here will be the two parts. And of course, we're multiplying AX and BX here. So in this case, we've multiplied AX by BX, and we are treating AX as a signed number. And that means that this is effectively a very large negative number. So again, you can see all of these bits have been changed to 1 here because that is a negative number. So you can see that we've effectively multiplied minus 32768 is that, and we multiply by that by hexadecimal 10, and that's the result just there. Now, if we treat it as an unsigned number, 8,000 times 10 is of course 80,000 in hexadecimal, and you can see that's happened just here, and these bits are now 0. So again, as I say, when we do these multiplications, even though we never see AX and DX mentioned in this command here, the actual operation that's being performed is this one just here. So you do need to make sure you understand those commands when you're working with them. But as I say, very effective multiplication there, and it's kind that they're allocating all this extra space for us. We multiply two 8-bit components, and it's using a 16-bit component to store the result. We multiply two 16-bit components, and it's effectively using a 32-bit component to store the result. So that's quite handy there. Okay, so that's multiplication. Now multiplication isn't too bad. Divide is a little bit more uncomfortable for me, at least. So let's have a look here. Now, the problem we've got with division is if you've ever done any programming, you've probably heard of the dreaded divide by 0 problem. Okay, well, let's just discuss that for starters, because that might be something you have never really understood. I'll just assume you haven't. You probably do, but let's just assume it. Well, let's suppose you've got a cake, and the cake has 10 slices, and each person eats 1 slice per minute. Well, if you've got 2 people eating the cake's going to get eaten in 5 minutes. If you've got 1 person eating the cake is going to get eaten in 10 minutes. If you've got no people eating the cake, how long is it going to take for the cake to get eaten? Well, it's going to take forever. It's going to take an infinite amount of time because there's no one eating the cake. And that's the problem with division by 0. The answer is infinity, and you can't store infinity in a register. Unfortunately, in my sense of the thinking, this tends to cause crashes rather than causing duff values, which I know you can argue which is the better result, but I find it quite annoying. So what actually will happen on the 8086 is it will cause an interrupt trap, and this will basically crash the machine. So we need to make sure we're not dividing by 0. We'll actually see that in a moment. So that's the first problem, division by 0. That's a very common one. The other problem is that division might cause an overflow, because in the same way as before, where we were multiplying two 8-bit parts and storing the result in a 16-bit part, we're doing the other way around now. So we're dividing a 16-bit part and storing the result in an 8-bit part. So let's say you've got a value of 32,000 and you're dividing by 2. Well, the result is 16,000. You're not going to store that in an 8-bit result. So again, unfortunately, the way that things work, you might have a valid value, but you're actually, the way the mathematics is working and the registers are being used, it might actually be failing. So you do just need to make sure you're using the correct register types, and you're maybe checking your values aren't 0 and things before you do these commands, because otherwise you're going to have to deal with interrupts, and that's far more work. So as I say, I think what's going to be best for you is just to make sure, if you're using these commands, that you check your values before you start using them and just make sure they're going to be valid. Anyway, that warning out the way, we will try these and we'll just prove they fail later, but let's just fire these up and let's see the idiv and the div command, which again, idiv is for signed numbers and div is for unsigned, and again we can work with 8-bit values or we can work with 16-bit values. Now, when we do a division, it won't necessarily be the case that the result will be a whole number value. For example, if we're dividing 103 by 10, the whole value will be 10, but there will be a remainder of 3. And that's the way things work here. When we do a division, for example, if we are dividing AX by BL, because we've specified BL here, then AL will be the whole number part, and the remainder part that couldn't be divided will be AH here. So we do need to look at both parts when we're actually working out our values, and that's going to be the case for 8-bit numbers and also for 16-bit numbers. And so again, you want to check the cheat sheet and make sure you understand what each register is going to be storing when you run these commands. So let's fire them up and let's have a look at what happens here. Okay, so we've loaded in FD83 here into AX, and then we're loading 10 into BX here. And what we're doing here is first we're going to divide AX by BL here. So we're going to divide FD83 by 10 here, and the result is going to be stored in AL, the low part, and you can see that the result is D9, and then the high part is going to be the remainder. Now in this case we've divided minus 637 by hexadecimal 10, and the result is minus 39, remainder 13, and you can see here I've put the correct hexadecimal equivalents here, so you can just confirm that, and you can see that the remainder has been stored in AH, and the whole number division part, the successful divisions, has been stored in AL there. So that's how that has worked there for 8-bit. Now with 16-bit, it actually divides a 32-bit value by a 16-bit value, so it's using DX as the high part and AX as the low part. So in this case we've got all of these bits set to 1 here, and this is the equivalent of minus, and so this is the equivalent of minus 66,173, and then we're going to divide that by hexadecimal 10 again. And so the effective result of doing this idiv bx here is we're going to divide dx-ax as a 32-bit pair by bx, which is just 10. The result will be stored, the whole number result will be stored in ax, and the remainder will be stored in dx. It's a real pain, this, very confusing. So here's the source value here, and the remainder here is minus 13. As you can see, I've just noted this, I had to do all this in a calculator, and the whole number part, the successful divisions, is minus 4,135, which is EFD9 here, and you can see that's stored just here. So when you do that division, you get that there. Now those are all a bit of a pain, and they're very hard to make sense of on screen. Fortunately, the unsigned ones are a lot easier. So here we are. This time we're going to do the division of a 16-bit number here by the 8-bit number here. So we're loading in D83 here. You can see D83 here. Now we're dividing that by 16 here, and this time we can much more clearly see what's going on. So we've got AH here is the remainder, and AL is the whole number part that was successfully divided. So D83 was divided by hexadecimal 10, so the whole number part was D8, and the remainder was 03, and you can see the 03 is there and the D8 is just there. So that's worked as expected from that there. And then of course we can do that with a 32-bit part divided by a 16-bit part. So we're dividing 1 FD83 here by hexadecimal 10, and the whole number successful part was 1 FD8, and the remainder was 03. And as you see here, the remainder is stored in DX, and the whole number part was stored in AX. Okay, so those were a little bit confusing. I certainly found them quite confusing. So I'd suggest, hopefully you'll be able to work with just unsigned numbers, because these signed numbers are very strange. But okay, so we've had a look at those. Now, I think the next thing we need to do is we need to just see what happens when things go wrong. So let's try doing this divide by 0 here, and we'll just see what happens here. Now you can see the first line, which is the test here, but then the second line results never came out, and what's actually happened here is an interrupt 0 trap has occurred, and that's why we've got no results. I did try and do some trapping of those interrupts, but I was having a hard time. I couldn't really find any documentation on how to really do it, so I didn't want to cover that. As I say, my best recommendation would be that if you're doing things, just make sure the values aren't going to cause an overflow or a divide 0. So check the value's not 0, or either use 16-bit registers even if you think you might only need 8-bit in most cases, or alternatively just check the values before you run the command at all. So this one's the overflow one, and again this is just creating a value that's too big to be stored in the AL part that should be storing the value here, because we're dividing 1683 by hexadecimal 10. That's going to result in 168, and that's not going to fit in AL. So we've caused an overflow there, and again we've got a crash and we've got no result. So as I say, that's the perils of multiplication and division. So there we go. Hopefully you're not going to need them too much. You know, as I say, you're bound to need multiplication and division at some point. I'd suggest you just have a look at the commands to make sure you're using the right registers and you understand where the values are going to go and what size they're going to end up being. It's just a little bit of a pain compared to something like the 68,000 where you've got the 32-bit registers for everything. It's a little bit more tricky, unfortunately, on the 8086, but that's just the way that it is. Okay, so now we're going to move away from mathematics and we're going to have a look at another test here. So this is actually going to make some sound for us, which is a bit of a change. This isn't a tutorial on sound, so we're not going to discuss the details of it. What it is we're discussing ports. Now, ports are something that happen on all hardware, of course. These are where we communicate from the processor to other bits of hardware, for example, a sound chip, or maybe a keyboard, or even a disk drive. So we have on the 8086, very similar to the Z80, we have this concept of numeric ports, and we can send data out to a port, so we can send a value to a piece of hardware, or we can read in from a port, and we will get a value back. So in this case, we will either send a register out. So for example, here we're sending the value in AL out to port 43 in hexadecimal, or in this case, we're reading in from port 61 hexadecimal into AL here. And so these are transferring a byte of data to or from these numeric ports. Now, what do these numbers mean? Well, you got to check your hardware documentation and make sure you know what it means. We're not going to cover that in this series. We're going to cover it later in the platform specific series, because it's platform specific. This is just talking about the processor. So that's why we're not doing it here. But anyway, so here we are sending the value in AL to device 43. Here we're sending the value in AL to device 42. And here we're reading in from device 61. And you can see I've put some documentation here of what these actual parts are doing. Here we're selecting a counter and we're sending it to this device. Here we're sending an actual tone effectively. And in this case, we're just waiting for the keyboard controller status here. So as I say, we're not going to cover how this works. We'll do it in a later one. But it was just to say for the out command, sending data to a device, the in command reading data from a device. And so let's fire this up and let's just see what happens. So we've got a tone there and then it's stopped. And I think if we change this tone, so there we go. Anyway, I say we're not going to cover how that actually worked. We're going to do it later on, just to discuss in and out there. Now, one other command we will talk about at the same time is the no operation command. What does no operation do? Well, no operation does nothing. It does nothing at all. It's a kind of dumb command. It just sits there for a moment and goes, okay, well, we'll carry on. Now, in this case, we've used it as a crude delay. In other cases, if you're doing self-modifying code that reprograms itself, this is something big in 8-bit programming, you might want to use that to replace other commands with a dummy command. And so I just needed to cover it. It's a short delay in this case. command that does literally nothing. So there we go. That's what we're going to cover on those then. It was just a good opportunity to get into ports and also cover no operation. So the final one we're going to discuss is we're going to discuss interrupts. Okay, well, what are interrupts? Well, interrupts are when an event occurs and the processor stops the running program and actually has to do something else. Now, in the case of interrupts on the 8086, these are at low memory addresses, and these are effectively a jump to another part of the code. Now, we had interrupts occurring when we were causing our division by 0 and our overflow, and we can actually reprogram those if we know what we're doing, and actually we can cause them artificially, and we're going to use that for a little bit of a test here. This isn't something we're going to go into in a great detail. I just wanted to give a brief coverage of it, and mainly to discuss the interrupt command, in which case we can actually cause an interrupt to occur at times of our choosing. Now, the first one we're going to look at is interrupt 4, which is the overflow from a division. We're going to actually replace that interrupt handler, and the way we do that is we need to know the address of the interrupt handler, which we've got here, and we need to write a code segment, and that's just going to be our current running code segment, and then we need to write the offset for the program counter for when that interrupt occurs. And when the interrupt occurs, the processor will read the code segment and the new program counter and jump to that code immediately, and we don't need to do anything else. So what we've done here is we've created an interrupt handler which just shows int4 and then does a return here with iret, interrupt return, and we can then actually cause that interrupt to occur by putting an interrupt command and the number 4. Now, in this case, of course, this was actually being used before by the division command, but we can now use it as our own special thing, and maybe we could use it as a monitor tool. Now, that's how we can override an existing interrupt, but the other thing is there is a special interrupt handler which could be quite useful to us, which is known as the step trap. Now, this is effectively when we set a certain flag on the processor, this interrupt occurs every single command as the processor operates normally, and we can use this for monitoring certain sections of our code and seeing what's going on, like if our code's malfunctioning, for example. So what we're going to do is we're going to put a trap in that's going to show the value of AX using our usual do monitor call here, and so we're loading that in again here just by overriding these addresses, which are for interrupt 2, which is the debugging step. So these are the fixed addresses, and we're loading in the segment of our running code and the offset of our running code, which means effectively that this will be executed every single command when that flag is set. Now, the way we need to set the flag, there's no special command to do it. So what I've done here is I've pushed the flags onto the stack, loaded the stack pointer, set the bit in the value on the stack pointer, and then pop the flags back off the stack. So that is a bit complex, but that is effectively set the trap flag that we can't set in any more direct way really. And then this trap will occur every single one of these commands, and then finally I've turned it off here, and it will actually run for a couple of those as well until the flag is cleared. So for every single command during the time that that flag is set, a call will occur to this command here, which could be quite handy for us debugging. Okay, so let's fire this up and let's see what happens. Okay, so the first part of our code here was setting up the interrupts for us to play with here, so you won't see any results of that. That's just setting up the two here. Then we've got these two int4 commands which have effectively caused a call to this routine here, and you can see that they've both shown an int4 here. Okay, well then we turned on our trap flag here, and you can see here when this command executed we got a dump of the values of AX here because a call occurred to this trap here. So you can see 1, 2, 3, 4, then 5, 6, 7, 8, then 9 ABC, and then you can even see a call here 0, and then another one will have occurred here 0, and then it stopped, and our last line here AX, BX, CX, DX, this is the normal do monitor command here. So you can see that there were 1, 2, 3 extra AXs here, all of which were 0, and that's for the execution of these 3 commands until the flags were cleared again. And then once the flags were cleared, you can see there's no more such results being exported. So there you go. So that's just a very brief introduction to how we can actually change the interrupt handlers, the int command for forcing an interrupt to occur, and also the iret command for returning from an interrupt. And they were just really some things that you're probably not going to need, but I do really want to try and cover all of the fundamental commands of the 8086 so that you at least have heard of them and you know about them if you come across them in someone else's code, or if you're reading some of the documentation, you hear them mentioned and you don't know what they mean. Okay, so there we go. We've gone over a variety of things today, a little bit more tricky stuff and not necessarily stuff you're going to need for the simple stuff, but again, things we needed to cover. I hope you found this interesting. We're still going to do one more tutorial on the 8086. We've got some stuff on strings and things. So, please follow along, like and subscribe if you've enjoyed this. The 8086 tutorials aren't proving as popular as my other ones, so please make sure you do that if you want to see more of them, because I am going to make tutorials based on what people are enjoying, and these are some of the least popular tutorials on my channel, so make sure if you want to see more you do like and subscribe. Anyway, I hope you've enjoyed this. I hope you enjoyed programming the 8086. Once these tutorials finish, we've got loads more coming. We're going to be programming the DOS machines in VGA, EGA, CGA, and also the Wonders one, because that is an 8186. Anyway, I hope you've enjoyed this. Thanks for watching today, and goodbye.